Okay, so last time we left off right here, so picking up, so I want to take our formula for a linear approximation right here, and I want to manipulate it around a little bit. But before I do, let me just remind us, we actually did accomplish something previously where we actually now know that this formula makes sense. That this formula is not going to be some sort of nonsensical garbage that seemed like a good idea at the time, but actually crashes and burns. And the reason why is because now we know that we should only use this for differentiable functions. And furthermore, we have a precise definition of what differentiability means. And furthermore, and arguably more important for us, we know how to confirm differentiability. And of course, in all practical circumstances, confirm continuous differentiability. Much easier to work with, and it gives you the same punchline. Okay, so what are we going to do with this equation now? And really, this is just a simple rewrite. First of all, easily confirmed. And in fact, one of our requirements for the idea of a linear approximation is that L and F agree at the base point A. So let me just rewrite F of A as L of A. No big deal. And now let me take this and move it over to the other side of the equation. Okay, hardly anything happened there. But what we have now is a really valuable rewrite, new interpretation that we can take from it as to what this matrix is. This matrix, you could previously have thought of it as a participant in the formula for linear approximations that kind of makes stuff work out in seemingly a reasonable way or something along those lines. It plays a role kind of analogous to the derivative. Okay, but here's a much, I think, more succinct interpretation. This is what you multiply by however much you've changed in the input. This is what we call the input differential. df is what you multiply by that input differential to get, well, our linear approximation of the output change, which is our definition of our output differential. So now this is succinct and crisp. df turns input changes into output changes. And you may recall that when we were first talking about our very first sort of dipping our toe in the water of multivariable derivatives, we eventually started off with partial derivatives. But before all of that, I pointed out that in some sense all derivatives have to be relationships between input changes and output changes. df is the general answer to that question. It does not require some silly, impractical, only one variable is allowed to change at a time. No. Whatever. X and A could be any direction. Doesn't matter, right? That's how life works. You don't get to just change one little thing at a time. That's not how reality comes at you. This also, better than the gradient vector, because this does not assume that your function is real valued. Gradients only make sense if you have a real valued function, one output value. That's it. Right? So this is our general relationship between input changes and output changes. So my hope is that when y'all leave this course and someone says the word derivative in reference to a multivariable function, I hope that this is the thing that you think of, the derivative matrix. In general, this is what plays the role of the derivative. And arguably, in some sense, everything else is kind of a special case or a contributing element of or something like that. This is really what the derivative is. So be aware of that terminology. And sometimes, of course, we call it the derivative matrix. It's reasonable. Sometimes it's called the derivative transformation because what we do with the derivative matrix as a matrix is we use it to turn input vectors into output vectors. In other words, we use the fact that it is a linear transformation. So also a common terminology. Okay, so just to put a picture on what we're talking about here, here is the sort of the little graphic. Again. Now keep in mind that what a function does is it takes an input point, such as A, and it turns it into an output point, f of A, right? And so keeping in mind the function turns an input point into an output point. That's what f does. But df does something different. df takes an input change, thought of as a vector, and produces from that an output change, thought of as a vector. So df, again, turns inputs into outputs, but not points representing literal, actual, inputs to the function. But df does it to changes, or thought of as vectors. df multiplies an input vector and produces an output vector, both representing changes. All right, how are we doing? Does everybody buy that? Everybody see how it is ultimately a very natural interpretation of df, and in retrospect, kind of something that we really needed, right? We already had the function f that takes an input point and gives me an output point. Now we know how to take input changes and linearly approximate output changes. Okay. All righty. Now, here is a tweak of that. Keeping in mind, here's the formula that we were just looking at, previous page. What if everything's a function of t? What if our location in the domain here, we're momentarily at the point A. What if it's not just that I'm going to jump to a nearby point, end of story? What if I am continually moving? What if I have an instantaneous velocity at the point A? And I want to know, as I move in the domain, what is my resulting instantaneous velocity of my image? And here's the good news. You can take this equation and just divide by dt, like you'll see I've done there and there. And then that purple equation literally turns into this equation right here. And notice that equation does kind of morally the same thing. This equation expresses how the derivative matrix, right, turns what is now an input velocity very conveniently into an output velocity. It's pretty handy, right? And so again, now it's still kind of morally the same idea. The df matrix is turning an input vector into an output vector, but now this input vector doesn't have to be thought of as some discrete, finite, instantaneous jump, right? It can represent a continuous velocity, and the output vector can be thought of as the resulting velocity of the output. All right, so I think that's nice too. Most of the time, frankly, when I'm thinking about the derivative and what does the df matrix do, I tend to think of it in terms of velocities and not in terms of changes. And the reason why is because this is exact. And in particular, this is the actual rate of change, the velocity of the output. It's not a linear approximation of the rate of change of the output. It is a limit. It's an instantaneous thing, therefore it's a limit, and so it's exact. Whereas, here, this interpretation here, this df thing is, it's not really the actual how much the function changed. It's just our best estimate of how much the function changed. And that sloppiness makes me a little less happy. This, I think, is really, really nice. Okay. All right, now last comment here. This is more a notational point than anything else. It's just a recognition that I could go through that same argument that we just did, but I could do it for real valued functions. And when you're talking about a real valued function, remember that instead of the derivative matrix, you instead could use the gradient vector, and specifically dot product with the gradient vector. And so the punchline then is that dot product with the gradient vector again turns turns input differentials into output differentials. So now, again, this is a peculiarity of real valued functions. It's got to be real valued if you want to use this alternative sort of point of view, where you're not multiplying by a matrix, you're dotting with a vector. So, is this importantly different? And if so, how do you decide when you should use the one, when you should use the other, right? And the answer is this is really not different. Ultimately, this is a lot like this observation. You may recall this old observation from linear algebra, and that is if you have two vectors, transposing the first vector to view it as a row matrix and then multiplying it by the second vector is literally the same arithmetic, and so you get the same result as doing a dot product. Right, and that's really all that's going on here. So viewing this as dot product with a vector is like the v dot here. And if you were to take this gradient, right, and transpose it, you get exactly the derivative matrix of that real valued function. So ultimately, it's all the same stuff. And you'll even notice that the coordinates, the elements of the derivative matrix are, well, just exactly like the elements, the coordinates of the gradient. It's all the partials. Just all the partials. If you make them a row matrix, that's the derivative matrix. If you make it a column vector, that's the gradient. Other than that, it's all the same. Okay. Moving along, same interpretation then, that what the gradient vector does, dot product with the gradient vector, just like the DF matrix, it turns input changes into output changes. And of course, this only makes sense. You can only, wrong color. You can only use dot product with the gradient vector if it's actually real valued. Only one output value. Otherwise, there is no such thing. Okay, so moving along, talk about a couple of properties of differentiation, multivariable differentiation. The first thing I'm going to say is it's linear, and a lot of people take this kind of the wrong way when I say that differentiation is linear. A lot of people think I'm talking about the DF matrix. And of course, now the DF matrix is, being as it is a matrix, obviously linear. Okay. That's not what I'm talking about when I say differentiation is linear. This is linear in the sense that if you take a linear combination of input vectors, then you get the corresponding linear combination of output vectors. So here's what I was actually talking about when I say differentiation is linear. The act of differentiation, the act of taking a differentiable function and producing a derivative matrix df. It's not just that the df matrix itself is linear. Again, that's a freebie. All matrices are linear thought of this function. It's that this purple thing called d is linear. Right? So in other words, when you are talking about a linear combination, again, not a linear combination in the domain of df, but a linear combination in the domain of d, right? In this green space, a linear combination of differentiable functions, that you get linearity as well. So one pithy way of making the distinction here is that I'm distinguishing between the result of differentiation versus the act of differentiation. Everybody see the distinction there? So of course the result is linear, is a matrix. But furthermore, the act of differentiation itself is linear. So let's see an example of this in action. And here's a couple of functions. You'll notice that is a differentiable function, and this is also a differentiable function. I have two differentiable functions. And I can talk about their derivative matrices. That's no sweat. We can compute their derivative matrices. Here's the derivative of f. Here's the derivative of g. Fine, no problem. By the way, make sure that you can actually do this. Right? Make sure you can produce those derivative matrices. Always worry about transposing. Right? You got to remember columns play a very special role. Rows play a very special role. You got to get that straight and not accidentally backwards. Okay, now what if I did this linear combination of those two functions? Right? Before I do any differentiating, I take a linear combination of those two functions, which gives you this. And now let's talk about the derivative of that linear combination. Well, the derivative of this linear combination, again, this is a matter of writing it down, taking the appropriate partials. There it is. Right? And did linearity work out here? And yes, it did, as follows. Because if I were to take the 5, 6 linear combination of the individual derivative matrices, right? So this is the linear combination of the outputs, you might say. Notice that I get, indeed, the same thing as the derivative of the linear combination of the input functions, right? And that derivative of that linear combination is that thing that we had there. So the linearity works because that you get the same thing either way, whether you take the linear combination before you do differentiation or whether you do the linear combination after you did the differentiation, same thing either way. Okay. So neat fact, a little bit subtle, important thing to know. All right. Now I'm going to do a quick hand wave. There's again, I have to do this because we're always in a rush in this class. I can't spend class time on everything, but there is a product rule. There's actually a couple of different product rules and a quotient rule. They're in the book. I'm going to say they're pretty unsurprising. So take a look, right, and notice the form that they take. And think about the circumstances that make those equations work out. You might even consider the possibility of checking that they work by kind of working it out by components. There's just a little bit of tedium. There's no real surprises on that road. But anyway, good to know there is a product rule and a quotient rule. And so heads up and take a look. Okay. All right. So higher order partials. Now this is another sort of like expected thing. I mean, y'all did second derivatives in Calc 1 way back when, right? And sure, if you have a function, you take a derivative, that's also a function. You could take the derivative of it. Same story here. This is a function of two variables. I could take an x partial. That too is a function of two variables. So I can take the x partial of it, or I could take the y partial of it, either one, whatever. And so this is a partial of a partial, otherwise known as a second partial. Okay. Now the notation is a little clunky. Let's talk about that just for a quick second. The x partial here, if I take the y partial of that x partial, well, of course, this is how I would write that. I mean, here's the x partial, and here's how I write my taking the y partial of that x partial. And that motivates this kind of combined notation here. You notice that the dy is on the left, and the partial y is on the left, partial x is on the right. That's just how it lays out. Okay. But here's the thing. I could have written my x partial like that, and then the act of taking the y partial of the x partial would be a subscript there on the right, because that's how we write subscripts. That's just, it just is, right? And this kind of suggests this notation. F sub xy, indicating again the x partial was first, the y partial was second. And what's super awkward and very unsatisfying in a way is that these two notations here, seemingly at odds with each other. The first one is on the right there, but it's on the left here. And the second partial is on the left here, but it's on the right there. And oh my God, that's super confusing. Right, so all I can say here is heads up. That's the way it is. I mean, and by the way, this really is also the way it ought to be. I mean, if f subscript x subscript y, if we were to write that as yx, that would be worse, I think. Right? So just be aware that there's just a direct incompatibility with these two different notations for differentiation. One of them acts on the left, the other one we write it down as if it acts on the right. And so of course these are going to be inconsistent. So heads up, don't accidentally misinterpret, and that's annoying. All right. Okay, now, neat coincidence to observe. fxy and fyx happen to be the same for this function. Not a coincidence, as it turns out. This happens, I'm going to loosely say most of the time in the kind of experiences that y'all are probably going to have, certainly in most of the experiences you'll have in this class. Most of the time, these are the same. And why is that? It turns out there's actually a pretty, it's a sophisticated discussion as to why that works. But here is the punchline. This is just clunky notation to describe what we've already seen this example of. All this says in clunky notation is that whatever order you have your differentials, if you rearrange the order, thus indicating that you're taking all the same partials, but you're just doing those partials in a different order, you will get the same result either way. Now, there is a condition on this. This does not always work. This only works for functions that are what we call CK, where K indicates how many partials total you're talking about. So what does CK mean? CK, well, the C stands for continuous, and the K tells you how many of the partials, in addition to the function itself, must also exist and be continuous. So C1 means that the function has to be continuous, but also the first derivative has to be continuous. Or for a multivariable function, that all of the first partials must be continuous. C2 means all the first partials and all the second partials must be continuous. Okay, so that's a strong condition. It's also a bothersome condition because if you think about it, if you've got a function of 5 variables and you want to talk about a mixed third partial, there's 125 different third partials of a function of 5 variables. And this would suggest that you have to compute all 125, confirm they exist, confirm that they're continuous. And that, of course, is wildly impractical. Right? Nobody is suggesting that you would actually do this. Right? So here's the workaround that applies most of the time. Huge categories of functions at a glance, you can easily determine have partials that are all in that same category, and that's good enough in most cases. For example, let's take a polynomial. Any polynomial. I don't care how many partials you take of any polynomial, the resulting partial will also be a polynomial. Polynomials always exist and are always continuous, and so bam, we just confirmed that polynomials are not only CK, they're what we call C infinity, because you can take as many partials as you want. And they'll always be continuous. Does everybody see how that? So very often it's just pretty direct observation. Okay, so nice. what does this look like geometrically? We're going to start off with talking about the XX and YY second partials. Let's start with XX. When you compute fxx, remember, y is constant. But in particular, y is constant both for the first partial that I'm going to take and for the second partial that I'm going to take of that first partial. So when you're computing fxx, y is just constant for the whole calculation. And that being the case, I can totally draw a picture of this. If y is constant, all right, well, y is just going to be fixed at whatever value that is, and I'll be apparently just going in the x direction. I'll be looking at this cross-section in the x direction. That cross-section will be some curve, let's say about like that, right? And taking the second derivative with respect to x, well, we already know what the geometric interpretation of the second derivative is. It's concavity. And as I have it drawn here, this is concave down. Well, concave down tells me then that fxx is negative in this picture. Does that make sense to everybody? And, I'm going to say this is good news. This is what you would hope the answer would be. And sometimes stuff just works out, and that's what we've got here. Okay, now analogously and quicker on the this second time, let's talk about fyy. Well, for fyy, x is constant for the entire calculation, which means that, okay, fixed value of x, and we're now just going to look as we go in the y direction, and thus in this cross-section, where the cross-section looks like this, and again, we're taking a second derivative. Y is our only variable. This is morally a single variable second derivative, clearly concave up, and that means that fyy is positive. That makes sense to everybody? Same idea, just kind of turned sideways. Okay. Now, one thing that is weird about this and unfamiliar from single variable calculus, at this single point, right, at this one point in the domain, the graph is both concave up and concave down at the same time. There is no single variable version of this, right? It's both. It's concave up in the y direction, it's concave down in the x direction. This kind of weirdness is what we now, in some sense, there's enough kind of room to move in the domain. The domain's two-dimensional, and there's just more room for functions to get weird. This is just one example of an oddity that there's not enough space for in single variable. So heads up for that. Okay. All right. By the way, please also notice what a good job I did drawing that Pringle. That's harder than it looks, right? I was very proud of that. I cheated, by the way, in that drawing. I encourage you all to do this too if you ever need to draw something, a function that looks like, but there was one on the homework you may recall where the function was kind of sloping down in one direction but kind of up in the other direction. And I literally Googled a picture of a Pringle and then I kind of traced it. Right? So, something to think about. Okay, here's where things get even weirder. How are we going to make sense out of what we call a mixed second partial? So, like so. The x partial of the y partial. Now, I'm not going to be able to use the argument that we did moments ago. Moments ago, we were like, hey, x is constant for the whole thing, man. It's okay, nice and simple single variable calculus. Not so here. Here we're taking the y partial first, we're meaning that x is constant for that y partial. But then when we get around to doing the x partial, x is no longer constant. Now x is the variable. And y is constant, which had been a variable previously. Right, so this is definitely different. This is not a, kind of relatable to single variable. This is a new concept that does not have a single variable analog. All right, so how are we going to make sense out of this? Here's what I'm going to do. This is the best way that I'm aware of to make sense out of this. I'm going to interpret the y partial as the slope of the graph. Specifically, keep in mind we're looking at a function f, so let's presume we have a graph of the function f. We'll think about what this looks like on the graph of that function f. And so I'm going to be interpreting those y partials as slopes of tangent lines. Now, how are we going to interpret the x partial that I'll be taking? And we absolutely cannot view this as a slope because we're not taking an x partial of f. Right? We're taking an x partial of the y partial of f. That's not the same as f. So I don't have, 2 seconds, I don't have a graph of the thing I'm taking the x partial of. So I can't use calculus of graphs to understand this partial derivative. Yeah?
So if you think about it like conceptually,
Mm-hmm.
isn't a y partial just like the change of like the y, like the component of the y component of rate of change?
So I think you're thinking of it kind of backwards here. So the point is x and y are both input variables, right? So it's not like x and y are functions of t like in a parametric curve. See, when you have a parametric curve, then you can talk about, as you move along the parametric curve, then there's kind of a y component of the change, and there's a sort of an x component of the change. So what you said would make sense in that, but we're doing it sort of the other way around. This is not one input variable with x and y being the two outputs. This is x and y are the two inputs, and then there's just the one output.
Okay.
Does that make sense?
Yeah.
Yeah. Okay. But good thinking. Yeah. Okay, so we have to figure out how to think about this x partial. We don't have a graph of that thing, and so slope is off the table. So what we're going to have to do is try to imagine, try to remember what other interpretations do we have of x partials, and specifically the one I'm going to talk about is x partials represent a rate of change as you move in the x direction. So that's what we're going to be doing here. We're going to be thinking about, as we try to understand the x partial of the y partial, we're going to visualize the y partials as representing slopes in the y direction, and we're going to understand the x partial as meaning how fast are those y slopes changing as I move in the x direction. Okay, so let's actually rubber meet the road here. If I can get this thing to okay, there we go. Okay, so now I've drawn a kind of a picture here. You'll notice pretty conspicuously missing from this picture. I have not drawn the actual graph surface itself. I tried. It's just too hard. It ends up being more confusing, frankly. And so use your imagination. I'm going to go through and describe what I did draw, and as I talk through what I have drawn here, you can try to visualize where that graph surface is and what that graph surface kind of looks like. Okay, so starting off, what are the y partials? Where are the y partials in this picture? Well, again, they represent slopes of tangent lines as I move in the y direction. So, for example, here I am moving in the y direction, and let's suppose that the tangent line to the surface, which I didn't draw, but the tangent line to the surface, let's say, for example, it might be like that, right? So the slope in the y direction, that to my eyeball looks like it's about -0.5, something like that, right? And I could do the same thing at other points. I could talk about, as I move in the y direction there, well, there will be some slope of the tangent line. And as I move in the y direction there will be some slope of the tangent line, blah, blah. Likewise, here and here, there will be various tangent lines with various different slopes. Yeah?
Is the slope of this tangent line always going to be on the yz or the xc plane? So it's like going to be perpendicular to the y-axis?
I am not exactly sure what you're asking here. So the idea is, let's take this one right here, right? So at this point, you can see I'm moving in the y direction,
right?
And if I were to think about a cross section, like a vertical cross section that is in that direction, then that would give me a curve to which I can talk about a tangent line. And I'm just saying that this would be the tangent line sitting above that line there.
Gotcha.
So I'm not sure if I answered your question. Is that
Thank you.
okay? Yeah, cool. All right. Okay, so those are the y partials. Now, the y partials are not what we're interested in. Notice what we actually are interested in is the x partial of the y partial. So keeping in mind, I'm interpreting the x partial as how fast are these y partials changing as I move in the x direction. So I have to look at this picture and imagine as I move that way, as I come out of the page, right, as I go, as I've drawn on the blue arrow there, as I'm moving that direction, how fast are these green y slopes changing? Now, let's just kind of talk through it here. Looking at this one right here, that would appear to my eyes to be about a -2. Right? This is about a -1. This is about a -0.5. This is about a 0. This is about a +0.5. Now, let's kind of put it all together. As I move down this line, as I go in the x direction, notice my y slopes are increasing. Everybody see that? Okay, well let me say that a little bit differently. As I move in the x direction, these green objects of the x partial are increasing. So said differently, that x partial is positive. So what we have here is a picture of, and let me kind of clear up my mess here. What we have here is a picture of this mixed partial being greater than 0. Said differently, now here's where I'm going to ask you to use your geometric imagination and imagine what kind of a surface is it for which the y slices have these kinds of cross sections. And my best shot at explaining what this looks like is that it's kind of a twisted surface. And I keep looking for where to find a sheet of rubber about this big so I can make an actual visual aid, but I don't know where to find such a thing. But imagine that I've grabbed that sheet of rubber by the 4 corners and that I put a twist in it about like this. Everybody see kind of the twisting that I'm doing here? And notice by twisting it, I'm going to get these negative slopes kind of in the back, right? Because of this part. And then as I do that same twist, you notice I'm getting these positive slopes in the front. So a positive x partial of the y partial represents a twisting on the graph. Sometimes referred to as torsion. Yeah, which, whatever. Okay, so it's a nice exercise to think for yourself. Okay, well, what if the x partial of the y partial were negative? What would that look like? Right, that'd be one to think through. What if you're taking the y partial of the x partial? How would you visualize that? It'd be analogous to this, but everything would be kind of sideways in the other direction, and it'd be a nice exercise to try to draw that picture and think about what that would look like. Okay. All right. Okay. Moving along. Let's see here. Oh, we're tight on time here. Okay, so section 3.1 is the next thing we're going to do. We have not finished chapter 2. I have a particular point of view that I like to do on chapter 2, specifically on section 2.5 when we start doing the chain rule, which will be on Wednesday. There's a particular point of view I find extremely helpful, and it involves derivatives of parametric curves. So I'm going to jump forward in the book to section 3.1 where they actually do derivatives of parametric curves. We're going to talk about that here, and then when we get to section 2.5 on Wednesday, I'll be able to use the tools that I think are really valuable. Yeah.
Where does the concept for the test on Friday
that's going to depend on how much we finish today, and it'll all be on the class schedule. And I'm going to send out an email clarifying. It's technically all on the web page, but just to make sure everybody's on the right page, I will email about that before I go home today. Yeah, right. Okay. Okay, so let's talk about parametric curves. This is a parametric curve. Recall its position as a function of time. And throw one variable in variables out. We can write down the derivative matrix. There's only one input variable, and therefore there is only one column. And what we would have expected to be partial derivatives that would go here, well, there's only one input variable. There is no other variable to hold constant. So, in fact, these are not partial derivatives. These are just good old, plain old Calc 1, old-fashioned derivatives. And thus you'll notice I'm using the D's instead of the partials. Okay, so what if we hadn't thought of the derivative matrix? What if we had developed these ideas in a different order? And by the way, in some textbooks, including mine, I do the ideas of derivatives and what kind of derivative come first in a different order. I like, not that it matters, to start with parametric curves. And you can just describe the derivative of a parametric curve, no problem. Here's the old Calc 1 formula for a derivative. Nothing to it. You can subtract. You can divide by h. It's all good. Because there's only one input variable, all this works out and makes sense. Okay? So conveniently, notice we get the same thing either way, right? I mean, here I'm doing the derivative of the entire vector-valued function all at once. Here I'm doing the derivatives one coordinate at a time. Whatever. So very conveniently, the idea of a derivative matrix in this context is this point of view right here. Really is a nice way to think about what it's actually doing. So now what does that actually represent? Oops, too far. Here we go. Let's kind of draw the picture. Now, first a quick warning. A lot of people are going to look at this and be like, oh, good. Oh, yeah, cool. Slopes. It's not. Can't interpret this as a slope. Because in Calc 1, when they talk about how derivative means slope, again, what they never say but always mean is slope of the graph. We are not looking at a graph. We're looking at a parametric curve. Parametric curves we draw by literally drawing the outputs. When you draw a parametric curve, you're drawing the image of the function, not the graph of the function. Said differently, when you're drawing a parametric curve, you don't draw the t-axis. If it was a graph, there would be a t-axis. There is no t-axis. Right? Does that make sense to everybody? So, totally different kind of a picture. We're going to get a totally different geometric interpretation. So please don't make that mistake. Very common mistake to make is for students to say, okay, well, this is a single variable derivative, so it probably means like the slope of the graph or something like that. That's not what this is. Okay. All right, so what is it then? Well, these are 2 points on the parametric curve itself. The difference is that displacement vector. When I divide by h, I'm going to get a vector in that same direction. A little shorter, right, for values of h that are above 1. Of course, now as h gets smaller and smaller and smaller, these 2 points get closer and closer to each other. This dark blue difference vector gets shorter and shorter and shorter, but then I'm dividing by smaller and smaller h. Right? And so just like in single variable calculus, those forces tend to balance each other out. And in the limit then, when you're talking about what is the limit of these kind of green vectors, the limit is just going to be a vector that is pointing tangent to the curve instead of secant to the curve. And now that tangency is kind of a familiar idea. Right? It's kind of just like it sounded in single variable calculus. So that's a little bit of good news. But very importantly, the answer is a vector. So the derivative of a parametric curve is this vector right here. Now, a couple of geometric observations to make. This vector, you'll notice that it's a tangent vector. It is pointing in the direction that and my pen picks as I'm in a hurry to finish the class. That's when it's going to die. Okay. Sorry. Okay, so the direction that it's going is the direction that the derivative points. That's convenient. What is the magnitude? Let's think through what the magnitude of this derivative is. Well, the magnitude, let's see here, magnitude of x prime. Well, I can take those magnitudes, put them on the inside. There's some little formalities there. I'm going to sweep under the rug. Hope everyone's willing to believe me. That's legal. It's perfectly fine. Then, if you think about it, is just giving you the distance between these 2 points. Right? The magnitude of a difference is the distance between those 2 points. What I have down here, that h, is literally the amount of time in between when I was at the first point and when I was at the second point. So altogether, the magnitude of the velocity vector is distance divided by time. And in the limit, that gives us what we call speed. Okay, so altogether, we actually have a really nice answer as to what the derivative vector is. Let's see, where am I? Here we go. This derivative vector, it's a vector that points in the direction we're going, whose magnitude is the speed. That is the definition of velocity. Right? One of our very first examples of vectors, in fact, is the idea of a velocity. So, really cool interpretation. It is not a slope, right? But when you're looking at a derivative of a parametric curve, the derivative is the velocity. And there's an analogous argument that you can make if you're so inclined. And the second derivative, namely the derivative of velocity, is the acceleration. Okay, so this ties in very nicely with those old physics ideas. Let's see here how we're doing on time. We have 2 minutes. Okay. Let me pause real quick. Questions? Anybody have a question? Everybody all right? Okay. We're not going to have time to finish this example. Maybe I'll just do the very first little bit of it because it's very straightforward. You might even recognize old Calc 1 questions of this sort. And that is if the velocity and the initial location are given, how would you compute the acceleration? How would you compute the position function? Right? And there's again, you've done these in Calc 1 classes. So it's morally the same thing here. We already know, in particular, that that velocity, when you take the derivative, gives you the acceleration. So great, take the derivative. Nothing to it. There you go. There's the acceleration. We also already know that velocity is the derivative of position. And now let's say the same thing backwards. That means position is the antiderivative of velocity. Right? So trying to find position, we'll take an antiderivative of velocity, and we're not going to have time to finish that up, so I'm going to say we draw the line right there, and we'll pick up there on Wednesday. Okay, see y'all later. Have a good one. Don't forget to talk to me if I haven't gotten you down for attendance yet, and see you later. And I'll send out an email about fair game material.